Hello and welcome back to Climate Plus, Purpose and Prosperity in an Unprecedented World. And that unprecedentedness includes ever more extreme weather and ever more dependence on our energy infrastructure, especially our electric grid. So how do we create resilient energy infrastructure?
My email down so we don't get any more noise. Sorry about that.
My guest today, Hal Corin, is innovating at the cutting edge of this challenge for a battery company called Viridi. Before Viridi, Hal was vice president and global head of energy and sustainability at 𝗵𝗵𝗀𝗆 in their global real estate group, overseeing strategy, development, and operations of sustainability, energy efficiency, renewable development and procurement, global utilities, water conservation, and physical decarbonation ambitions of 𝗵𝗵𝗀𝗆's global real estate division. Hal also sat on the advisory board for the World Green Building Council. Wow. Welcome to the podcast, Hal.
Thank you, Lincoln. Great to be here with you. Thanks for having me.
So let's start at the very beginning and thinking about an audience that is very smart, but may not have a full understanding of what energy infrastructure is and how we depend on it and what's the state of play today.
Yeah. Well, that is the very beginning. So let's go back. Sort of the model that the U.S. electric grid was built within, or maybe the paradigm would be a better word than the model, was really designed in the 1880s, 1890s. And most of that build out occurred post World War II, really in earnest in the 90s and 60s. And so, right, the paradigm we're talking about is few really large centralized generators that send out high voltage power over transmission systems. You step it down somewhat locally, and then there are distribution systems from there. So the US power grid is often referred to as the largest machine in the world. You know, something like 150,000 or 200,000 miles of transmission lines, millions of miles of distribution infrastructure. You know, look, it was built with intention to have a 50-year life. And if you call the cutoff point, or when most of it was built at 1950, it's 75 years old. And we have considerably more diverse and growing and divergent needs to the paradigm that it was built under. And so, you know, I think about like a 1980s car, right? Like, take that car, plop it into today, and put all the new requirements on it. So sometimes we need it to run backwards. We need it to be much more safe. We need it so, you know, collapsible steering column, shatterproof glass, seat belts,
Airbags,
anti-lock brakes.
Yeah.
What was yours?
I was going to say airbags too.
Airbags,
massive change.
Yeah, you know, kind of all these things, and then there would be better like marginal things, like we're not going to use drum brakes in front and back, and all of those things. So, you know, there's almost no limit to the intricacy that you could sort of go in on there and sort of set your new requirements. You know, to me, that car from the 1950s, if I picked, I would go with the C1 Corvette, 1957. You know, right? Like, what does that car look like now? To me, it's probably unrecognizable, but you know, what does it cost to implement all of those things? Twice what the car costs, 5 times, 50, 100, you know, right? Like if I'm putting all of those in a C1, which I probably couldn't even fit in, but you know, Lincoln, what's your 1950s car that you would pick?
A Porsche 356 coupe
Okay.
And there are many generations for the Porsche files out there, but I'd go with the coupe.
Right. So both of our vehicles are like 4x in size and who knows what. But you know, the point is, like, instead of doing all of these bolt-ons and retrofits and the customer being ultimately unhappy at the end of it, let alone it being semi-impossible to do the work, you know, it's time to realign on what we're solving for. And going with the car analogy, right? We're trying to get from point A to point B. Translating that highest level for grid, We want lower cost, high safety, higher reliability power for the long haul.
Yeah.
And we want to potentially create opportunities where we lower risk for customer, off-taker, and utility, and build more confidence in the American economy and ways for infrastructure to not limit economic growth and prosperity. And so, the good news is that there's a solution that prevents all of these massive, highly expensive infrastructure upgrades that are tough to rate base, tough to get consumers excited about because it means their bills are going to go up a lot. Enhances reliability, lowers system costs, increases efficiency, increases utilization of generation going into the mix, and creates a lot of opportunities for those at the edge. And so, in that sense, what we're really talking about are distributed energy resources, and batteries are kind of like the alpha option of all distributed energy resources, because instead of sort of participating in the grid at a sacrifice to what you're doing within your building, a battery serves as that buffer. I bought a battery exactly for this purpose. Whatever you need, grid, I'm going to provide, and I'm not going to sacrifice my businesses or my home's critical need during those critical grid hours.
Yeah.
And we think about like hottest hours of the year, those often coincide. Grid needs AC and to power AC just when I need it, whether I'm at home, business, or at a healthcare facility or an art museum or somewhere else.
Right. Right. So let's talk a little bit about that. There are a lot of different options. And when, for the non-energy geeks out there, when we say behind the meter, we mean behind the meter at the edge that basically separates the system from your house or your factory or your office building or what have you.
Yep.
So behind the meter is like putting solar on your roof. Behind the meter is putting a battery in your basement.
Yep.
Is putting an emergency generator, for example, just outside the building. Can you talk about the various options there and how, everything's got compromises. How should we look at those various options, I guess, in and of themselves to serve the building, but also as part of the larger grid equation?
Yeah, I can tell I'm going to get myself into trouble with this answer. The first thing that I'll say is just like the paradigm of the grid that was built out, at this point, like 120, 130 years ago, the reference point for all technologies and the infrastructure is very utility centric, right? The early customers were like, hands off, I'm buying power. Your job is to enable economic growth. My job is to pay you for the juice that will power my operations or my home. And so in that sense, the meter is a construct. And so it's used as a delineating point where you can make one measurement. Of course, solar challenges this. One measurement of the flow through it. And that's what you're charging your customer for, period, full stop. But in reality, there are rules that have kind of sprung up and are associated with that. So in a lot of parts of the country, there would be limitations to what grid revenues you can participate in or grid programs based on your proximity to the meter, before or after, behind or in front of. And so in that sense, like there's this sort of artificial limiting of, we're not going to recognize your value because of where you sit, on a one-line diagram, but also physically.
Yeah.
But when you think about moments of grid collapse and extreme weather events, they're actually regulatory structure or regulatory policies that prevent a battery or a different asset that's behind the meter from providing benefits to the neighbors of that facility. And so I'll get off my soapbox and maybe answer the actual question. It manifests differently in different places. So I guess to start, behind the meter means with the customer's load. So if you're a building or a home, it's behind the meter with you. And so, what that means is that if you have a battery next to your home or facility, you could be drawing off the grid at the same time you're drawing other power to power the building at peak, which is unlikely because that would be really expensive. Or you can begin shifting where that draw occurs to be off peak and maybe use it as a load shift scenario where you're charging up the battery at low cost times on the grid, or where there's excess, depending on where you are, that could mean a lot of different moments. And you discharge when you really need it, or your cost of power, or perhaps demands on the grid itself are most intense. So distributed energy resources can come in a lot of different forms. Solar is one, ability to dispatch any load is one, being able to reduce load is a DER, and I would argue similarly, being able to determine when on a rolling basis is most optimal to turn on a load is also a DER, because sometimes the grid needs us to take off excess and sometimes it needs us to put back.
Yeah. So many options there. And to me, the big distinction, the primary distinction is behind the meter, are you generating power, for example, with solar on your roof, or are you just storing power? So absorbing with the batteries, absorbing it, as you said, when energy costs are low, and then either using it or selling it back to the grid when energy costs are high. And there's a real struggle there. And we see this here at Stanford too, because we think about that in two ways. We think of it as energy arbitrage, essentially cost optimization during normal times. But then if we've got a heat wave coming, we're going to charge everything up. We don't have very many chemical batteries. We have some thermal batteries in terms of storing chilled water.
Big ones.
Yeah, and one of the things that has been challenging for us in terms of batteries as emergency generators is that if the grid goes down, you only have the amount of energy you have in that battery, which you're gonna run down over a certain amount of time. For example, with a diesel generator or some other sorts of fueled generation, you can, as long as you can get the fuel there, you can keep making electricity.
Yes.
And I wonder, how are you guys thinking about that kind of ordinary course arbitrage versus emergency coverage duration, I guess, sort of challenge?
So, I mean, this is a tough space, but the way we think about it is stacking as much value on any decision as possible. And so, on a daily basis with no grid infrastructure challenges, you would arbitrage the market or peak shave or play into a predictable revenue stream. But in moments of outage where, it could be, God forbid, there's wildfires coming, or there's a cold snap, or, it's the wind's blowing really heavily during storms and there's supposed to be a storm this evening. So it could be sort of any level of flavor of intensity where you want to be reserving capacity within your battery. So the way that I think of it is, fundamentally exactly like you said. But what you're worried about is, okay, I only have this many hours of what my usage is going to be within the battery. And so then what really helps is to consider, typical outage length and bring that into your sizing. So in most of the country, outage length is less than a few hours. We sell a 4 to 5 hour battery. And so if you look at instances where that would be adequate for you, you're probably okay 80-90% of the time off of the battery. But, in the same vein, you need a backup plan, especially if there's life safety or mission critical functions served behind your meter. And so in that case, you would either lean into existing emergency generators or have a service contract where, an equipment rental company is required or, has an agreement with you to show up with a battery with a generator or a battery, given a certain amount of outage. In microgrids where you have solar or some other generation source, this is sort of built in. And in that case, leads to a different result in sizing. The other thing I would say is, and we have a ton of experience in this at Viridi, where we run batteries plus diesel generators in hybrid mode, sort of in distributed microgrids. And so in that sense, we've done this for wastewater pumping stations and, events out in different deserts and harsh environments and construction sites and all these things. When you run a diesel generator or any combustion engine, it likes to run at full load. That's where its peak efficiency is. And most load or most equipment are sized based on peak and not really actual typical runtime, because your constraint is peak. And so you'll peak up here, generator's happy to run, but it's going to run typically at 20% or less load, where it's extremely inefficient, it's harsh to run, and it leads to kind of operation and maintenance challenges and wet stacking and all these problems and increased emissions. And so what you do is you run the diesel to carry the load and charge the battery. So you're fully utilizing the generator. So it's running at peak efficiency, it's happy, it runs for less hours total. You then shift to battery once it's fully charged. And then when the battery dips below the need for load, diesel fires back on and begins the cycle again. So there's this even intermediate step, whether you have permanent generators to couple with the batteries or temporary generators to bring in with the batteries, or they can both be mobile. But the point is that, like we were saying before, this is a moment where technology is actually kind of delivering on the future promise that we had hoped for.
Yeah. And I contrast that with what you were talking about earlier, which is this grid that we've built. First of all, based on assumptions from 150 years ago, but second of all, mostly built right after the Second World War, and thus an asset that was supposed to last 50 years is still going at 75 years. How do you find your customers? How are they thinking about the risk? How are they thinking? Is this top of the agenda, or is it more of a kind of, better lucky than good sort of strategy, or somewhere in between?
Yeah, I mean, I think it depends on what business you're in. Like if you're in the EV charging infrastructure business and you're just trying to get more sites turned on and they have immense power needs, like this is top of mind for you. You've got to figure out how to make this work. Similar if you're in the data center space, but I would kind of put everybody else in the, look, power costs rising at 20% annual is untenable for our business. Doesn't matter what business you're in, or if you're, even in a for-profit versus a nonprofit, government has this problem just like everybody else. So then it's like, it really becomes an energy management and a fiscal management kind of challenge. And, I think what a lot of large portfolio owners, particularly national or, beyond regional groups, deal with is, well, we've got 5,000 locations across the US, and you're telling me that my identical location in San Diego to the one in Des Moines to the one in, Tallahassee, if I drop a solution on each of them, I'm going to get a different result? What? That makes no sense to me. And so, like, then you get into this really deep education of like, oh, we have different rate structures and regulated and deregulated and all of these things. I think part of the challenge is it's so complicated. You kind of need, like, I don't know, a PhD or a master's level of fluency in this subject matter. And, all they're trying to do is, like, save money on my bills, de-risk a little bit, maybe decarbonize a little bit, but in some way hedge into the future and have a higher degree of business certainty and a lower degree of risk. And so, it's tough out there.
Yeah. And I can imagine there are a lot of things that, again, we energy geeks take for granted. Like, of course, there are different regulatory structures around across the country. Of course, there are different rate designs within the utilities within those regulatory structures. Of course, there are different motivations. I mean, an installation risk in Florida with, I don't know how many named hurricanes every year, 4 or 5, is very different from risk in San Diego, which is kind of the one of the world's weather sweet spots. How do you find customers looking at that with any level of depth, or do they just not throw up their hands, but do they just delegate that to a vendor like you and say, you guys figure this out and let us know what the right answer is. We'll ask a couple of questions and then we'll buy it.
Yeah. I mean, I would say we're really privileged to have the trust of our customers, and so in that way, we kind of put all options before them, or, preface our work with that ask. Like, okay, well, do you want to give me payback criteria and everything above that line is a yes? Or do you want to give me payback criteria and that's the average target, therefore we can go below the individually acceptable line, and maybe
Right.
instead of grabbing just 700 sites, maybe that puts 2,000 on your list, and we're still a net break even based on today's dollars, maybe without consideration of utility escalation that everybody at the table believes is going to happen. So there's sort of different ways to slice it. But I think, right, one of Viridi's key differentiators, and frankly, the reason that I came over, was they came up with a solution for thermal runaway in their proprietary anti-propagation architecture. That's a lot of big words in one. Essentially the outburst that's likely from the best energy cell chemistry, lithium ion, has this fatal flaw where 1 in 10 million, 1 in 40 million cells naturally will go into thermal runaway, which is an explosion, and then it causes a chain reaction and propagates into a fire that cannot be put out by water. Really horrifying. And so, for that good reason, batteries, particularly in substantive size, have never been allowed in or around buildings. And so Viridi's technology changes that. And so we're starting to see kind of the recognition of that go through different markets and parts of the country as we're scaling. And so from that sense, putting batteries in substantive quantities behind the meter is a new proposition. And so what we're really seeing with customers is they get it, that there's a financial, a resiliency, maybe a decarbonization, I don't know if we're still saying sustainability now, benefit to these things. In parallel, there might also be, a time to power play. But in a lot of cases, this is the first battery installation an owner will have done. So, it's a lot of like, we're going to dip our toe in the pool with several sites before we unleash the whole portfolio. And so, when we perform, of course, doors open up really, really widely, which is exciting for us to bring customers along. And that's a good, genuine interaction. Like, let us prove it to you, and then we'll go on from there, holding hands for the whole portfolio.
Yeah. Can you give us an example, without naming names or anything proprietary? Can you give us an example of what a maybe you don't have a standard installation, but what an installation might look like, so that people can kind of paint a mental picture of that?
So let's say you have something like a small format, small commercial, like something the size of post office, or a Taco Bell, or a bank branch, or something like that. And so our base battery building blocks are 50 kilowatt hours and 10 kW charge and discharge. A small commercial facility, probably peaks annually around 30 kW, I would say is average for US. So you would need 3 of those building block kind of large suitcases in order to fully offset your peak load draw. Now, that would be 150 kilowatt hours for 3 of those units. That 150 kilowatt hours would power the typical American home for probably 5 or 6 days.
Really?
Yeah, so just to give kind of a sense of like what's in the tank. And so from there, the question is really indoor or outdoor for this installation. If it's indoor, you would really look for the corner of a utility room, or maybe if there's a basement. Hopefully it's right next to the electrical room, and you can sort of hook the batteries in there and put in your the energy management system brain, and kind of have everything run nicely and easily. The good news is there are no moving parts in these systems. So in a way, it doesn't really matter where they're sitting. They'll still work the same way, but of course, clearances and inspections and all these things, back of house is better. Or you could go with, we would take those same 3 units, 150 kilowatt hours, 30 kW, and we would mount them on a skid. So those together would probably be the size of a large desk or half of a parking space, like 7 feet by 3.5 feet in footprint. That could go next to the building, just outside next to the electrical panels, hopefully next to the service entrance, or in sort of a back of house area behind restaurant or whatever the commercial building would be.
Mm-hmm.
In that installation, maybe there's solar on the roof. So, part of the game would be, let's save up our excess solar and save it for dispatch when the grid needs it, or when we'll save the most cost on the building's energy consumption. In a lot of cases, you would use it for peak shaving or sort of discharging the battery to avoid those peak moments that are most costly for most commercial energy users. And then you could get into more complex things, within tariff. If there's a time of use rate structure, you'll have a very straightforward way of running the battery. We're going to charge up between midnight and 6 a.m. and we're going to discharge between 6 p.m. and 9 p.m. It's a California example. But, if you have exposure to the real-time markets, you could arbitrage against the real-time pricing, or do arbitrage against local carbon emissions for a decarbonization outcome. And really the answer is the revenue streams and value streams are kind of limitless, but they are growing, they are maturing. And the one thing I say to every customer is, the only thing I can guarantee you is that the rate structures are going to be different in 5 years than they are now, and they will be more different in 10 and more different in 15. Because we're in this phase of grid evolution and no signs of stopping, at least yet.
Yeah. And so I want to spin it, before we get to the lightning round, I want to spin it all the way back to around to the beginning. So how does this antiquated end of life, beyond end of life power grid, how does it play nicely with a battery behind the meter? Is the grid, I always think of the grid as designed for a one-way transfer.
Yep.
It's a one-way transaction. The utility sends power and a bill. Money goes back the other way. And we've gotten increasingly, we got to a point where all of a sudden we had, say, solar installations behind the meter selling back into the grid, so more of a bilateral thing. And now we're almost in a multilateral situation where there are other players, aggregators of all these loads, all these storage devices and generators and demand response, as you pointed out, behind the meter. How does battery fit in? And I know, actually, I'm going to give you one more caveat, and this is the longest question in the world. One more caveat is that, of course, every utility is different. Every state regulatory construct is different, regional constructs. But just in general, how do you get a battery to play well with the system?
Yeah. Well, the good news, I was at a dinner at RE Plus a few weeks ago, and I was sort of sitting with a partner and then with a customer that I hadn't met before. And I'm listening to the conversation, and I was in the lucky seat of, they knew what problems that they were dealing with and had active projects kind of everywhere. And so every 5 minutes I would, come out of being quiet and I would say, batteries are great for that. This happened like 4 or 5 times, and it's like, just talk to me and I'll give you the use cases.
Mm-hmm.
So, it turns out that, I'll give an example, right? As intermittent renewables, so solar or wind, kind of penetrate markets further, you have voltage drop, and it becomes really difficult to manage the actual grid properly and keep, the sine wave of the power curves at a level that they're not burning up equipment and, really causing problems. And so batteries are something that clean up, the sine wave and power curves. And so you have to know how to use them for it, or rather the grid has to be asking for those DERs or specific DERs to respond in that fashion, but they help. Other grid services, like if you think about aggregators, say just grabbing demand response contracts, for that same 30 kW size of a building at the peak hours of heat in the summer, like how much can you turn down? Like, well, We still need to keep it comfortable here because we're a commercial enterprise, and we certainly can't give you half. We're open.
Right.
Maybe we can get you 3 kW, 10%, and that would be a lot. If that same site has a battery, we'll give you 30 kW, no problem. We'll own the whole facility for you, and we can guarantee that that's not a problem until the tank runs out. So in Viridi's case, 4+ hours. So batteries quickly become this sort of dream resource for utilities, for, local distribution grids. So maybe that's a municipal utility or a co-op. But, we need this two-way communication and sort of transparency and honesty in our constructs where the grid operator is communicating clearly with the aggregator or the customers of, this is what I need from you. This is what I'm going to need from you tomorrow. And by the way, this is the amount of value that it has to me, and I'm going to give you half, or I'm going to give you 30%, or I'm going to help you invest in that resource so that I can use it for my benefit sometimes. And it's like those sort of dynamic exchanges that help new projects and assets come about that are really the promise of a lower cost, higher reliability, higher equity grid, kind of that we've all hoped for in our best system engineered view of the world. And so, more of these are popping up, but there's, I've been in energy management at this point for over 10 years, and like batteries have always been the dream. Safety has always been the problem.
Yeah.
There's no more valuable place for batteries to be located than next to load. Just like solar is most valuable, batteries make solar more valuable by making it dispatchable and controlling it and providing buffer. But as we look into grid transition and electrification, higher constraints, batteries become even more clearly needed. And I would say, to the credit of the industry, folks have realized that in mass. When you go to these like big conferences like RE Plus or these various climate weeks or DistribuTech, you kind of have an understanding of, the nice way to say it is the buzz in the room. The maybe not nice way to say it is what is everybody freaked out about this year? And so, I would say for the last 2 years, it's been like, how do we get batteries done? How do we get them behind the meter? How do we get more of them? And of course, now there are more geopolitical considerations related.
Yeah. Well, that's a great place to segue to our lightning rounds. 3 questions, same questions I ask every guest. So the first one is the opportunity question. So if you had $1 million, $100 million, some big chunk of money to invest in the solutions that we've talked about and in enabling the solutions that we've talked about, where would you put that next chunk of money?
Yeah, let's call it 100 million instead of 1 million.
Sure.
I think I would want to go to maybe a municipal utility or to a co-op and say, let me put adequate quantity of batteries behind the meters near you to provide for all of the flexibility your grid is going to need currently to be most efficient, to lower your cost of operation, lower your cost to do critical upgrades, lower cost to customers, and for the next 5 or 10 years. And so it would be sort of a fixed contract to solve your problems for our benefit and for everyone else's benefit. Would sort of be the pitch.
Yeah. So the second question is kind of the mirror of that, and that is, if you had a giant metaphysical bulldozer that you could bulldoze away one big impediment to getting all this done, what impediment would you bulldoze away?
Yeah, that's a tough one because it's like, I can make my wishes, but hopefully it's something that could actually come true. This was something I saw when I was running energy management for a really large school district. We put in real-time meters at all 175 of our properties, and they had 1 second level granularity. And we did this for a few $1,000s each installed. And off of that high granularity data, I was able to not only build like an M&V, measurement and verification program, where I could show the benefit to the school board and to the students, I reverse that order for preference. Put students ahead, of like what the value of their energy conservation or their behavioral savings programs or the solar we just put on the roof provided. And so you make it tangible. But on top of that, I hired a programmer and we created real-time based weather normalized behavioral energy saving competitions that schools could compete with each other on. And so, but zooming out from that, with granularity comes, actually being able to inform people what's happening and to be able to see it. 15-minute data, you can't identify a chiller fault that's firing every 1 minute or, technically, right, how just the way mathematically averages work, every peak you've ever seen on a utility bill is much lower than it actually is. Wouldn't it be nice to know where your peak is actually happening so that you can
and how high it actually is? Yeah.
Yeah, right? Like, technically it could have been a peak of 1,000 for 1 second, or it's a peak of 100 for 10 seconds, and you don't know the difference. That's big.
Yeah. Yeah. Yeah.
So, what I would say would be most of the utilities in the United States operate, some not even to this level, off of 15-minute interval data. And that's how they determine where your monthly peak or your annual or seasonal peaks occur. And that's the highest granularity that can be shared with customers. But at the same time, all power in the US that's distributed is managed at 60 hertz, which means, 60 times a second. So we have the technical ability to do more, and, we're just not providing that data or, digitizing enough. And I think the opportunity that this provides beyond informing all stakeholders, when we're managing to the nth degree, which we must in order for the system to not be subject to, daily or hourly collapse with all these new priorities that are, 1950s, was it a 356?
56, yeah.
Yeah, with our nice, 12-ton 356 with all these new features on it to keep going, right? Like, we need to actually know what we're solving for and be able to pivot intelligently with machine learning or AI, moment to moment to moment.
Yeah.
And with granularity at each site and source.
Okay, last question. It's the spotlight question. If you had a giant spotlight that you could shine on something that is underknown, underappreciated,
yeah,
that you really wanted the world to focus on, and it's not focusing on it, where would you shine that spotlight?
Yeah, I think really on order of magnitude of the types of grid growth that we're expecting. So, a lot of people have said, and of course this is absolutely correct, that part of the challenge in where we are now is that we've not professionals in the space who know what they're doing and utilities companies who get it have never gone through a period of grid growth. And we're starting to experience this. But what are the sources, right? There's onshoring or bringing industrial America back to the US. Or industrial. Let's remove the industrial America part back.
Yeah.
So there's bringing jobs and industry back to America. There's, of course, AI and data center load growth. There's electrification of transportation, EVs. There's electrification of heat. And then I think there's sort of this unknown factor of, we're going to be using more equipment. We don't know what it'll be for. There are more TVs in restaurants when we go to them now, or sports bars or whatever. There are more outlets in classrooms. It's sort of like this unknown tech adoption curve also. And so, everybody is in a tizzy over AI load growth, and that's big. But, estimates show that of our grid that consumes around 4,000 terawatt hours annually now in the US, AI load growth is projected at, on average, something like 400 terawatt hours of growth by 2030. If we look at electrification of transport, that's really a doubling of the entire grid. So that's like 8,000 and change equivalent terawatt hours. And yeah, we're probably not going to convert all of that, but it's going to be substantive and potentially 10x in magnitude, at least of where AI load growth will go by 2030. Now, if you look at electrification of heat, that's something like 5,500 equivalent terawatt hours of heating gas or fossil of some kind that's dedicated for heating homes and buildings and industrials. And so, that's more on the order of a doubling, but you have to realize that you shrink that. It has a higher power implication than energy implication because it's only really cold in some places half of the year. And not all places get really cold. And the hours of the day that it's really cold are, different than the hours where the sun is shining. And so you end up in cold climates needing infrastructure-wise something, like maybe a 4x service size increase just to electrify. And the implications on something like, the sun doesn't shine as brightly in the winter and sometimes our panels are covered with snow while it's really cold out, are kind of destabilizing factors. So what I view as the next 5 years of grid growth in the US, very angled towards AI and data center growth, because AI and data centers currently spend 4 or 5% of annual cost on electricity. If you tell them that global supply chains are constrained, which they are, and infrastructure is really expensive, which it is, and the utilities have other things to solve for, which they do, they would pay double the cost, and they are, in order to implement this in the next 5 years. But it's palatable for them. This opportunity where we're going to undergo 10% net load growth in the next, it's about to be 4 years.
Yeah.
Is really the time to write the playbook and figure out exactly the right way to balance these different priorities into load growth. Because while EV adoption and electrification of heat and these other forms of load growth are going to be gradual and somewhat organic in how they scale, they're going to be not only bigger, they're going to be a heck of a lot bigger. And so we have to learn to tool in the right way so that we can meet those demands when they come and meet them in the best way possible to create equity, lower costs, a decarbonized future with lower commodity risk.
Yeah. Wow. Thank you so much for being on the program, Hal. This has been an incredible education for me, and I'm sure for everybody else. If you'd like to learn more about Hal and Viridi, check out, I'm not going to try to pronounce it, so I'll just spell it. 𝗲𝗲𝘀𝗶𝗴𝗆.com. And I hope you'll join us again for the next episode of Climate Plus, another set of challenges, opportunities, and solutions in our unprecedented Climate Plus world. In the meantime, you can find the podcast at 𝗏𝗏𝗄𝗏𝑝od.com, pretty much wherever fine podcasts are streaming, including YouTube, Spotify, Apple, and Buzzsprout, and on LinkedIn, Facebook, Instagram, and Blue Sky. If you've enjoyed this episode, make sure to hit that subscribe button so that you never miss an interview. Also, I would really appreciate likes, comments, follows, and of course, reposting and sharing the podcast with anyone who might enjoy it. It is a great way to help grow the Climate Plus audience. You can provide feedback to me directly by emailing me at leb@climatepluspodcast. Yes, different from the website. Mea culpa. leb@climatepluspodcast.com. Climate Plus is hosted by me, Lincoln Blevins, and comes to you from beautiful Half Moon Bay, California, just over the hill from Stanford University in Silicon Valley. Thank you so much for listening, and we'll see you next time on Climate Plus.